new discovery concerning Saturn. Ripples in Saturn's rings reveal a giant fuzzy core hidden beneath the surface. Michael Starr, Science Alert, reports, what's in a gas giant? No, really. The interiors of Jupiter and Saturn are actually quite difficult to probe, but Saturn's uniquely glorious and sensitive extensive ring system is proving to be an excellent tool for figuring out the densities deep below its thick cloud layers, right down to the core. That core, according to a new analysis of wobbles in Saturn's innermost main ring, likely is not a dense ball of nickel and iron as many think, but it is a fuzzy region of mostly hydrogen and helium, with a gradual mixture of heavier elements extending to 60% of the planet's radius and containing around 17 Earth masses of ice and rock. This finding is published in Nature Astronomy, and it's similar to recent findings about Jupiter's interior based on Juno data, and it could change our assumptions about Saturn's early structure and formation history. Caltech says the fuzzy cores are like a sludge. This is what planetary scientist lead author of the study, Christopher Mankiewicz, said. He said the hydrogen and helium gas in the planet gradually mix with more and more ice and rock as you move towards the planet's center. Kindly support my Patreon account since YouTube has again demonetized my YouTube channel. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below. It's a bit like parts of our Earth's oceans where the saltiness increases as you go deeper and deeper levels, creating a stable configuration. And this is the Caltech image, hydrogen, helium gas, and then you have the mix of ice and rock and metallic fluids, large wobbling core. Now, how can we learn that from Saturn's rings? It all has to do with the way rumbles, it has to do with the way rumbles in Saturn's belly influence the planet's external gravitational field. The scientists said, we use Saturn's rings like a giant seismograph to measure oscillations inside the planet. This is the first time we've been able to seismically probe the structure of a gas giant planet, and the results were pretty surprising. This is what Jim Fuller, the Caltech co-author, said. Acoustic waves and oscillations inside cosmic bodies are a brilliant tool for probing their interior structure. We do it here on Earth, where quakes send similar waves rippling through the planet. How these waves bounce around in there can reveal different densities, allowing us to identify structures that we could never hope to see. Now, on the Sun and other stars, interior acoustic waves manifest as brightness and fluctuations. Saturn is no place for a seismometer, and it does not undergo brightness and fluctuations, but a few years ago, scientists noticed signature patterns in Saturn's sea rings, the innermost of its main rings. These, they concluded, were unlikely to be produced by Saturn's moons, as such patterns are in the outer rings. Instead, they seem to be generated by oscillations deep in the planetary interior, which influence the gravitational field. Thus, the field of chronoseismology, Chronos is the Greek word for Saturn. The planet is called Kronos, so chronoseismology is Saturn seismology. This is what emerged, the study of Saturn's interior by analyzing these waves in the sea ring. Now, the Caltech team has conducted a new analysis of a previously characterized inner sea ring wave, whose frequency was much lower than expected of the established Saturn interior models. This frequency pattern, they found, places a stringent new constraint on Saturn's interior composition. Our models place tight constraints on the mass and size of the heavy element core of Saturn, even though the dilute nature of this core requires a more nuanced description than in traditional layered models. This is what they write in their paper. Based on these constraints, they infer that the mass of the core is around 50 times the mass of our Earth, containing 17 Earth masses worth of rock and ice, and the rest would predominantly be hydrogen and helium. The entire thing is diffuse and gradually mixed, rather than strictly delineated stratification with a denser concentration of heavier elements in the very center as we have here on our Earth. This poses something of a challenge for planetary formation models. It's thought that planets form from a bottom-up pebble accretion model in which small chunks of rock are electrostatically bound together until the planetary seed is large enough to gravitationally attract more or more material, eventually forming a planet. For gas giants, so like Jupiter and Saturn, heavier material was thought to sink towards the center, forming a solid core and letting the lower density gas rise to the outer regions. Recent models suggest more gradual distribution of material, or it's possible that convecting mixing results in a more gradual distribution. Even so, modeling formation pathways for a fuzzy core has proven challenging, and it's likely that more complex science jigging pokery will be required to fully understand how it can happen. That may be putting the cart a little before the horse, though. The new study is based on a C-ring wave. A little more chronoseismology, that is seismology of Saturn, would help validate the interpretation of the fuzzy Saturn core. This has been published on Nature Astronomy, published May 2021, and this is on Science Alert. Please leave your comments, and thank you for your support.